At the end of chapter 4, we obtained a profound result that energy is the generator of time evolution. Thus, we have discovered how to evolve our quantum state in time. The time-dependent Schrödinger equation, or TDSE for short, is exactly this statement. We have arrived at the fifth and last postulate of quantum mechanics. Quantum state evolves in time in accordance with TDSE. The time evolution operator is given by the equation displayed on the screen. The Hamiltonian is time-independent in the time evolution operator. TDSE is the conceptual equivalence of Newton's second law in classical mechanics. The solution of Newton's second law is position as a function of time, also known as a trajectory. The solution of TDSE is the state of the system at some future time. We now begin to solve the TDSE. We begin by substituting the eigenstates of Hamiltonian ket n for ket psi. The first-order differential equation has a rather simple solution. We now expand a generic state in the basis of energy eigenstates at some arbitrary moment in time, as energy eigenstates form a complete set at all time. Then substitute into the TDSE by differentiating the left-hand side with respect to time, then multiply by IH bar. Then apply the Hamiltonian operator on right-hand side to yield the equation on the screen. Cancellation of common terms on both sides yields the time derivative of the amplitude equals to 0. Thus, we have obtained the result that the amplitude in energy representation is time independent, thus remains constant in time. We have also solved the TDSE. The state at a future time t can be written as the equation on the screen. Hence, if we solve TISE of a system, we can evolve any arbitrary quantum state in time and understand its dynamics. This is why a lot of quantum mechanics is centered around solving the TISE. We are now in a position to demonstrate quantum mechanics is consistent with classical mechanics. We'll first consider the time evolution of the expectation value of an observable, as we have already established at the end of chapter 2 that classical mechanics is the mechanics of expectation values, where the quantum fluctuation around the average value is negligible. We write the expectation value in bracket notation, then use the product rule for differentiation. Then we substitute in TDSE and the summation adjoint to obtain the equation on the screen. Then we use the definition of commutator and divide through by IH bar on both sides to yield the Ehrenfest theorem. Thus, we have made our connection back to classical mechanics. We now justify our choice for generators in chapter 4. We assume the operator representing the observable of interest is time independent. This is usually true, as the spectrum does not change in time. The Hamiltonian governs the dynamics of the system, as it tells the system how to move forward in time. If the dynamics is invariant under symmetry operation, then the Hamiltonian commutes with the symmetry operation and the generator of that transformation. For translational symmetry, the translation operator commutes with the Hamiltonian. Thus, the generator momentum operator also commutes with Hamiltonian. And using the Ehrenfest theorem, we can conclude momentum is constant in time. This demonstrates it is the right choice to associate the conservation of momentum with translational symmetry and define momentum as the generator of translation. Similarly, for a system that is invariant under rotation, the rotation operator commutes with the Hamiltonian. Thus, the generator angular momentum operator also commutes with the Hamiltonian. And using Ehrenfest theorem, we can conclude that angular momentum is constant in time. This demonstrates it is the right choice to associate conservation of angular momentum with rotational symmetry and define angular momentum as the generator of rotation. Lastly, the Hamiltonian commutes with itself. And using Ehrenfest theorem, we can conclude energy is constant in time. This is another way of phrasing the law of conservation of energy in an isolated system. But also the dynamics of the system stays the same as we move the system in time, provided that the system is isolated. We now attempt to gain more insight into these energy eigenstates ket n by substituting them into the Ehrenfest theorem. and assume Q hat is time independent. Using TISC and the fact that Hamiltonian is a Hermitian operator to operate back into bra n yields the equation on the screen. The right-hand side vanishes, so if a state is an energy eigenstate, then the expectation value of all time-independent operator is constant in time. Another way of looking at this is that energy eigenstates are not localized in time, analogous to how momentum eigenstates can be anywhere in space. We shall also call energy eigenstates stationary states to emphasize this point. Stationary states are again an idealized mathematical construct, but they have a crucial role with constructing the solution of TDSE, so that we can easily evolve any realistic state in time. We now use the Ehrenfest theorem to evaluate the rate of change of expectation value of position and momentum to gain more insight into the connection between quantum mechanics and classical mechanics. The form of the Hamiltonian is constructed by analogy to the classical expression, kinetic plus potential energy. We first evaluate the rate of change of position by evaluating the following commutator between position and the Hamiltonian operator. Then we expand the commutator to yield the equation on the screen. Taking out the constant of 1/2m and noting any operator commutes with any functions of itself yields the result on the screen. Using the rule for expanding the product of operators in a commutator and using the canonical commutation relation to yield the commutator between position and the Hamiltonian operator equals to IH bar P over m. Finally, substituting back into the Ehrenfest theorem and rearrange to obtain the expectation value of momentum equals to mass times the rate of change of the expectation value of position. This is the definition of momentum in classical mechanics. Hence, our definition of momentum as the generator of translation is consistent with the classical definition. We now carry out the same calculation for the rate of change of momentum by evaluating the commutator between momentum and the Hamiltonian operator. We then expand the commutator and noting that the momentum operator commutes with functions of itself. And now, our job is to evaluate the commutator between the momentum operator and the potential energy operator, which is a function of position operator. The easiest way to do this is to evaluate the commutator in position representation. We right multiply by ket psi and left multiply by bra x, then expand the commutator. Then using the form of the momentum operator in position representation that we established back in chapter 4 to obtain the equation on the screen. Then we use the fact that the potential energy operator is a Hermitian operator to operate back into bra x to obtain the eigenvalue, which is the same function of potential energy of the eigenvalue x. We then use the product rule for differentiation to obtain the final result, which says the commutator between the momentum and the Hamiltonian operator equals to minus IH bar partial v by partial x. Then substituting back into the Ehrenfest theorem yields the final result. The right-hand side is the negative gradient of potential energy. We recognize this quantity as the classical definition of force, with force operator conveniently defined as F equals to minus partial v by partial x. We obtain the result that the expectation value of force equals to the rate of change of the expectation value of momentum. Hence, we have recovered Newton's second law. This demonstrates quantum mechanics is consistent with classical mechanics for large particles. This also demonstrates the form of the Hamiltonian as the sum of kinetic and potential energy is correct. Classical mechanics can therefore be regarded as a very good approximation of quantum mechanics at a macroscopic scale. Lastly, let us look at how quantum mechanics describes the dynamics of a realistic free particle. A free particle is not bound by potential, thus the Hamiltonian of the system is given by p squared over 2m. The momentum eigenstates ket p are also energy eigenstates and solutions to TISE. We can immediately construct the solution of TDSE by generalizing the solution for the discrete spectrum to the continuous case. Suppose the momentum of the particle is normally distributed around some mean momentum, p0, with sigma as the standard deviation or uncertainty in initial position. The wave function is given by the equation we used back in chapter 3 with a small modification. We then left multiply both sides by bra x to go into position representation, as we wish to see what is happening in physical space. Then substituting the results we obtained back in chapter 3 yields the time-dependent wave function as the following integral. After some tedious algebra, we obtain the equation on screen. The result is quite complicated, so we plot a graph to visualize the result. This is a three-dimensional graph, as wave functions have both real and imaginary part. The vertical bars connecting the curve to the x-axis is the modulus of the wave function. We can also calculate the probability distribution by taking the modulus square of the wave function. This is a normal distribution with time-dependent mean, mu of t, and variance, sigma square of t. Hence, the particle is traveling at a mean velocity of p0 over m, just as expected. To make sense of the increasing invariance as the particle evolves in time, we note that the initial uncertainty in momentum, sigma p, is h bar over 2 sigma from the end of chapter 3. This gives the extra uncertainty of h bar t over 2m sigma in position over time. This can be understood as due to the initial uncertainty in momentum, hence velocity, particles that are faster initially is further up ahead, and particles that are slower initially is lagged behind at time t. This is a perfectly sensible physical picture. To conclude, this demonstrates quantum mechanics is able to describe the behavior of a realistic free particle. However, the way it reaches to this conclusion is rather exceptional. We began by writing a realistic state as a quantum superposition of definite states of momentum and energy, ket p, which are neither localized in space or time. Then we evolved these unphysical states forward in time and constructed the final state as another superposition of these unphysical states. Lastly, we took the modulus square of the wave function and obtained something that is correct based on our mere physical intuition. Quantum mechanics is the most accurate and complete theory of the physical reality. However, it is amazing that no one really understands why the theory works, and many fundamental questions of the theory is left unanswered up to today. Thank you for watching.